Section 1.2, Solutions and Initial Value Problems. So what does it mean to be a solution to a differential equation? Well, if we think back to algebraic equations, the way we checked whether a particular value of x was the solution to an algebraic equation was that we plugged that value of x into both sides of the equation and we checked to see if we got a logically consistent statement. We're going to do the same thing with differential equations. So let's look at an example. Here we ask the question, is y equals e to the 2t a solution of the differential equation dy dt equals y? So in order for this function to be a solution to this differential equation, it should be the case that when we plug this function into the left-hand side and we compute what that left-hand side is, and we plug this function into the right-hand side of the differential equation and we compute what that right-hand side is, the left-hand side and the right-hand side should give us the same thing. Now it doesn't matter what that thing is, they just need to be the same thing. So let's check this. The left-hand side of the differential equation is dy dt, so that means we start with dy dt. Well, if y is e to the 2t, then that means we want to take the derivative with respect to t of what y is, and y is e to the 2t. Well, if we take the derivative of e to the 2t with respect to t, we get 2e to the 2t by the chain rule. So that's what the left-hand side is. Let's independently check what the right-hand side is. The right-hand side in this differential equation is just y, and then we just plug in what we are proposing y is, or what we're being asked what y is. Y is e to the 2t, so we're going to plug that in. There's nothing more to do, so we stop here, and now the question is, are these two equal? And no, they're not equal, and since they're not equal, that means that the original function, y equals e to the 2t, is not a solution to the differential equation. It's very similar that if you had the equation in an algebraic equation, if you had something like x plus 3 equals 7, and you wanted to know if x equals 10 was a solution. Well, you'd plug 10 into the left-hand side, you'd plug 10 into the right-hand side, and you'll see if the left-hand side and the right-hand side are the same. If they're the same, then that value of x is a solution. If they're different, then that value of x is not a solution. We're doing the same thing, except with a differential equation, it involves functions and derivatives of those functions. So let's try another one. This was a first-order equation, so let's try this on a second-order equation. We ask the question, is the function y equals cosine x a solution of the differential equation y double prime plus y equals 0? So we want to take the left-hand side of the differential equation. We want to substitute in what we're proposing the solution is. So wherever we see a y, we want to put a cosine x. And then we just let the calculus chips fall where they fall. We take the second derivative of cosine x plus cosine x. If we take the second derivative of cosine x, after a little bit of side calculation, we get that that is negative cosine x. Here, the cosine x is just cosine x. These combine to give me a 0, so the left-hand side simplifies to a 0. On the other hand, the right-hand side is already a 0, so we get 0 equals 0. These are equal, so yes, cosine x is a solution of this differential equation. Okay? So the next topic that we want to talk about is the concept of explicit solutions versus implicit solutions. And this is really more of an algebraic concept than a calculus or a differential equations concept. What we mean by an explicit solution, if you remember from algebra or calculus, an explicit solution or an explicit function is one where the dependent variable is nicely and neatly solved for in terms of the independent variable. So something like y equals 3x plus 4. Or y equals the cosine of 2t. Those are explicit functions because the dependent variable y is nicely and neatly solved for in terms of the independent variable. But you can have implicit solutions where the x's and y's are mixed together, something like the equation of the unit circle, x squared plus y squared equals 1. So that would be an example of an implicit function or an implicit relation. So what does this have to do with implicit versus explicit solutions? Notice here we're asking up here, we had this was an explicit function. Y is nicely and neatly solved for in terms of x. Up here, this is an explicit function because y is nicely and neatly solved for in terms of t. But now if you look at this one, the x's and y's are all mixed together. The dependent variable and the independent variable are all mixed together. So this is what we would call an implicit form. And so we want to know if this implicit form of this relation or function is in fact a solution to a differential equation. And when it's in implicit form, since the y is not nicely and neatly solved for, it's not immediate how we just plug this in. And so this makes the game just a little bit different than what we had before. So here's our game plan. Let's just stay philosophically consistent with what we did before. Let's look at the left-hand side of the differential equation, and we want to calculate what dy dx is. So if this is our proposed solution, we want to calculate dy dx of this, and we want to use implicit differentiation to do that. So we'll go ahead and calculate dy dx implicitly. So if you remember from calculus 1, if you have y squared minus x cubed plus 8 equals 0, and you implicitly differentiate this with respect to x, here we get a 2y dy dx, here we get a minus 3x squared, and then the derivative of 8 is 0, and the derivative of 0 is 0. And now we can solve for dy dx. This is just taking derivatives, no differential equations. And when we do this, we get that dy dx is 3x squared over 2y. We just solved for dy dx. So remember what we were doing before. We want to look at the left-hand side. The left-hand side of the differential equation is dy dx, but we just found dy dx to be 3x squared over 2y, so that's what the left-hand side is. And then we want to compare that to what we get on the right-hand side of the differential equation. Well, on the right-hand side of the differential equation, we get this. We ask, are these two things equal? Yes, they are. Since they're equal, then that must mean that this is a solution. It just happens to be in an implicit form. So y is not nicely and neatly solved for. The key point in all of these examples is that you don't have to know how to solve a differential equation in order to check if a given quantity is a solution or not. Now notice, in the interest of full disclosure, you had no idea where this function came from. You had no idea where this function came from. You have no idea where this function came from. But if you're given a differential equation and somebody puts a function on the table, you can determine whether that function is or is not a solution to the differential equation by following this procedure. And you can do it whether the function is in explicit form or if the function is in implicit form. And this is one of the reasons, there were others, but this is one of the reasons why implicit differentiation was talked about in Calculus 1, because you need it for the implicit form, checking the implicit form of solutions to differential equations. So you're going to see some in the homework like this where you're checking if a given function in implicit or explicit form is or is not a solution to a given differential equation. Okay, the next topic we want to talk about is families of solutions. So instead of being given one function to check if it's a solution, you could be given a family of functions. Normally a family of functions which has an arbitrary constant in it. So as a concrete example, suppose we consider the family of functions y equals a constant times e to the minus x, where c is an arbitrary constant. Right now, this might feel a little artificial and you're not really sure where the constant comes from. But notice this is a family of functions. They're all exponential functions. They just have different coefficients, where c could be any coefficient you want it to be. The question is, as a family, does this entire family solve this differential equation? Well, we're going to put it to the test. We're going to grab the left-hand side of our differential equation. That's dy dx. We want to calculate dy dx for this quantity. Notice this is in explicit form, so we're just going to differentiate this with respect to x. When we differentiate this with respect to x, we pull the c out. We differentiate and get e to the minus x times a minus 1, which gives us a minus c e to the minus x. We just set that off to the side. That's our left-hand side. We independently compute our right-hand side. Our right-hand side is negative y, so that should be negative c times e to the minus x. And there's nothing more we can do, so now we compare. Are these the same? Yes, indeed they are. They are the same because this is the same c here as we have here. Since these are equal, then that means in one fell swoop we just determined that this entire family of functions are all solutions to the same differential equation. So you'll see some in the homework like that, where instead of giving you a single function, they'll give you a family of functions. Okay, next we want to talk about the difference between differential equations and initial value problems. So remember, a differential equation, as we talked about in the last section, is just an equation involving an unknown function and one or more of its derivatives. So this is a differential equation in the unknown y. We're looking for the function y such that when you take its derivative with respect to x, you'll get x cubed. So this is just a differential equation. But we could ask this a different way. We could say, what if I had the differential equation dy dx equals x cubed, but I also wanted to know not just what y satisfy this, I also want to put on the constraint that y of 1 is 2. This is called an initial condition. Initial condition because we normally think of this as time, and we're giving some kind of starting value or initial value for our y. Geometrically, what this says is that whatever function, we want to find a function that satisfies this, that its derivative is x cubed, but we also want y of 1 to be 2, which says that the graph of y must pass through the point 1, 2. When the input value of x is 1, the output value should be a y value of 2. So notice this is really taking this differential equation. When we supplement it with this initial condition, then we have a differential equation together with an initial condition, and when you put these two together, we box this in and we call this an initial value problem. So it sounds a little fancy, but an initial value problem is just a differential equation together with some initial conditions. And here it's just one initial condition. Okay? So one other type of question that we may encounter is, suppose we have a family of functions and we want to see if this is a family of solutions for this differential equation. We've already done something like this before, but I'm going somewhere with this. So let's just check to see if this family is a family of solutions to this differential equation. And you don't know where this family came from, I just gave this to you. And to introduce a little bit more jargon, we call this a one parameter family of solutions. One parameter because there's one parameter or one arbitrary constant in this. So we want to check if this one parameter family of solutions, if this one parameter family is or is not a family of solutions for this differential equation. Right now there's no initial condition, just the differential equation. We're going to follow our script. We're going to take dy dx. That means we want to take the derivative with respect to x of what y is. Notice this is in explicit form, so we're just going to take the derivative. We take the derivative and the calculus dust settles, we just get x cubed. So the left-hand side is what it is. The right-hand side is x cubed, and then there's nothing we can do with this. So we just check and see, are these the same? Yes, they are. So since they're equal, that this is a family of solutions to this differential equation. So what if we took the same differential equation and we supplement it with an initial condition? So this is not accidental. I'm taking the same differential equation and we supplement it with an initial condition. So we're asking for a little bit more. We want to find a function that satisfies both the differential equation and the initial condition. And this is going to be a theme that we see throughout the course. First, we want to start with our known family of solutions. We're not wondering if this is a family of solutions. We just proved that this one parameter family is a family of righteous solutions to this differential equation. So we want to start with our one parameter family. So if you have a family of solutions and all you need to do is figure out, you want to solve the initial value problem, you want to start with the one parameter family of solutions, and then you want to apply the initial condition to lock down the value of c that will also satisfy the initial condition. So we're going to start with our general solution. We're going to apply the initial condition. So when x is 1, the y value ought to be 2. We plug a 1 in for x. We set the resulting output to 2. And if you notice, that's an algebraic equation in the unknown c. We'll quickly solve that. We get c is 7/4. This is not the answer to our question, but this does tell us that if we choose c to be 7/4, then this condition will be satisfied. We already know the differential equation is satisfied by this family of solutions. So we just wanted to see what value of c will also satisfy the initial condition. So if we plug this back in for c, not x, not y, we want to plug it back in for c, then this would be the solution to both the differential equation and the initial condition. And because of that, it's a solution to the initial value problem. So this is going to be a highly recurring theme for us throughout these sections is, if you want to solve an initial value problem, then first you want to get your hands on a one parameter, in this case, a one parameter family of solutions, and then you want to lock down the value of the parameter by applying the initial condition. And then this is not the solution that you seek, this is the solution. It's the value, it's the member of the family with the value of c plugged in, with the value of the constant determined by the initial condition. Okay, so that ought to cover you for everything that you need to see in this 1.2 homework. You're going to see some with checking whether you have an explicit function is a solution to a differential equation. When you're given an implicit relation, whether that's a solution to a differential equation. You'll see some with initial conditions, some without initial conditions. You'll see some with families and some that are single functions, but you ought to be able to do all of those now.